tap what?
Recording is on.
All right. Okay. Let's talk about Taproot. Tap what? So the presentation is it's not that high level. It's more it's a bit of details about the Bitcoin script and signatures. I think which is to the level of our team. It's not so much in detail that we're going to talk about Schnorr signatures too much and like the mathematics behind it, but we just have a little bit of math, just enough that I understand things and enough to blow your mind actually, because like Taproot is very cleverly designed. So let's get started. So there you go. So we're going to first I will talk about quickly how we spend Bitcoin output today. Quickly talk about Schnorr, Merkle tree, and math, and then we go into Taproot. Just want to give some information first before we jump into actual Taproot. So spending Bitcoin. So how we spend Bitcoin outputs today. So there's two ways. One way is pay to public key hash or pay to witness public key hash. So in transaction A, how is the pointer? I can't see the pointer. There you go. So transaction A output, you have the padlock is a public key, and you have a public key hash. Okay, so the mixer. So you don't see the public key, you just see a hash of it. And if you want to span transaction A and transaction B, then you have to reveal the public key that was hashed and attach a signature to it to show that you know the secret key relative to the public key. Okay, so that's how we do pay to public key hash or pay to witness public key hash if we use SegWit. Now, another way to span transactions or to span outputs is that we have is pay to script hash or pay to witness script hash. So this time, instead of having a pub key hash, we have a script hash. So there's a script, and we hash this. So we just see the hash. And then if you want to span this output in transaction B, then you pass the arguments of the script, which may be some signatures, and you have to reveal the full script. Okay, so that when you validate, you can validate that the hash of the script matches the script you are using to span the transaction. So what's important there? So far so good? Okay, cool. So downside with that, there's two downside. So first, you can see just from looking at the output, okay, in transaction A, just looking at that, the addresses for script hash and public key hash are different. So already when you do transaction A, you already know by looking at transaction A that the output will have to be spanned with a pub key or will have to be spanned with a script. So that's the first thing that you reveal. And of course, when you span the transaction, you are going to reveal the full script. So let's say we have a HTSC, then when we span, our HTSC output, we reveal the full script, which includes the, let's say we span it using the hash, but we still reveal that it is a HTSC, that there is a time lock component, and then the time lock component has said expiry time. Actually, on the other hand, I think the opposite is even better. More important is that if you use the refund path, so you use the time lock path to span a transaction, then you knew this transaction was for HTSC, and it was not, for sidechain or something else, or maybe it was not a fallback plan for some multi-sig system. It's exactly the script, and that allows you to run heuristics, both on transaction A when you look, he sends the money to a script or he sends money to a key, but also on transaction B, looking at, this is a 3 out of 5 multi-sig, and here are the 5 public key of the multi-sig because you have to reveal the full script. And by reveal the full script, it means that you have to put all 5 public keys in your full script. So even if you use three public keys to span the output, all public keys are being revealed with script. Another issue is the size of the script. So we say SegWit, witness is not included in the size and transaction fee, but it's still more data to exchange on the network, more data to process, read and do calculation against. So if you have a very complex script, which is quite big, then it's going to make it's going to take some more CPU and more data to have the transaction broadcasting and exchanged around the network. Okay. So far, so good on currently how we spend Bitcoin. Just ask your question in time. Let's talk about Schnorr. So Schnorr is a signature scheme. So let's maybe have a quick Schnorr versus ECDSA. So ECDSA or ECDSA is on the right here, is what we use today in Bitcoin. So first, why don't we already use Schnorr in Bitcoin? So historically, Schnorr had a patent until 2008. So it means that when Bitcoin white paper was released, the patent had just expired. Okay, which means that it was not really used widely. Whereas for ECDSA, it's open source since the 90s, means that it's been used a lot for SSL with SegP 256K1 being the one of the curve parameters for ECDSA. So it's been quite popular. libsegp was used already for SSL. So we already had 2 decades of industrial wide use in the wild. Okay. Now, in terms of mathematics, what's kind of interesting with Schnorr is that Schnorr only for Schnorr to be secure, only 2 assumptions are made. One assumption is that the discrete log algorithm problem is hard, which is basically your classic curve cryptography assumption, in the way that from a private key, it's easy to find the public key, but from public key, it's hard to find private key, curve math. And that hash functions are random oracle. So hash function are random oracle means that when you hash data, if you change 1 bit on the data, then the hash is going to be totally different. Okay, so you just assume that. ECDSA assumes the same, plus some other there's some other assumptions in ECDSA which I don't think they are proven so far. There always been some more papers recently, but I don't think they're proven. So what we mean is that Schnorr is probably secure, whereas ECDSA is not. I think it's quite a pedantic detail there, but everyone is talking about that, so let's mention it. In terms of public key and signatures, so here I'm talking. So this sizes is for Bitcoin encoding. Okay, I'm just talking about how we're going to encode it in Bitcoin. So ECDSA use DER or DR encoding, which gives you a 33-byte public key. And for signature, the signature on the right, is 70 to 72 bytes. For Schnorr, actually, we don't use DR encoding. It's going to be a direct encoding, actually, which gives you 32 bytes public key and 64 bytes signatures. So yeah, sizes are different. And with ECDSA, we use DR, which is like a special encoding, or like we process basically the data to encode it. Whereas for Schnorr, it's more or less direct encoding of the curve points. So with Schnorr, you have some feature which is called aggregation and batch verification features that I will talk about next. ECDSA, you don't have that. All right, so that's one reason why Schnorr is quite cool. And then for other signatures, so I mean, Lloyd and Lucas have mentioned that in the past many times, but it's much easier to do other signatures with Schnorr than it is with ECDSA. You can do it with ECDSA, but it's not as easy. I will not tell you how to do it, okay? All right. Next, so aggregation. So the aggregation, so I think you already all heard about it at some point, because I know that Lloyd mentioned it many times, and I think Lucas as well mentioned it. So we have Alice and Bob, okay? We have our Alice here, and she has a private key, so that's a private key, and Bob has a private key. So from this private key, they can derive their public key, which is padlock. And so what they can do is that they can add the public key, all right, in terms of Schnorr adding things. And this gives you a new prime public key, so public key prime. All right. Now, the magic thing is that Alice, using a private key, she can sign a message, and Bob can sign the same message, and you can add a signature, and this gives you a signature prime that is valid under public key prime. All right, and that's what's cool, huh? For me, for a few reasons. So if we talk about so multisig, so multisig is M out of M, so 3 out of 3 signature. It means that Alice, Bob, and Carol can all have their own private key, and you can lock something against the pub key prime, which is the aggregation of all 3 private keys. And then they can all sign the same message to spend it. And this could use signature prime, which is valid. And from the outside world, we only see a public key and a signature. We don't see the fact that behind there is 1 private key or 3 private key or 5 private key. You don't see that. And what's quite cool is for the batch verification. So it means that if you want to verify a lot of signatures, for example, transactions, then you can sum all your public keys of all these transactions, sum all signatures, and do one verification. So like signature verification is one step that takes a bit of processing to verify. But in terms of, you can do batch verification where you're just going to, so adding is cheaper. So you can add all your public keys and add all signatures and just verify that the sum of the signatures is valid against the sum of the public keys. And that will allow, improve performance. So aggregation is also called linearity, in case you wonder. So everyone clear on that? That's extremely important. All right, good. So let's talk about Merkle tree. So let's just talk about a standard Merkle tree. So like, without too much of Bitcoin context, it's basically a commitment binary tree. So what I mean by that is that I can just give a hash, which is the Merkle root. So this is a hash. So I can give the hash to someone and say, okay, I commit to some data, and here's the hash. All right. Now, when I'm asked to prove my commitment, and to say, okay, well, you committed some data, prove to me that it was part of this hash, then what you do is that you can just okay, sorry, I think let me restart the explanation. So how to calculate this hash first? So all the data that I'm committing to is A, B, C, D up to P. So that's data. Okay, I'm just going to hash every single item of data, which gives me HA, HB, HC, HD, etc. And I concatenate the hash. So I just put them together, so HA and HB together, and I hash this result, and this gives me HAB. Okay, and then I concatenate the hash, the HAB and HCD. So I put them, side by side. I hash this longer string, and this gives me HABCD. Okay, and that's how I calculate my Merkle root. So now when I want to prove that yes, K was indeed part of my Merkle tree, I just have to reveal K, and I can reveal all the blue boxes. So it means that the person that is going to verify can take K and hash K, concatenate HL and K, and calculate HKL, concatenate it with HIG and generate HIGKL, concatenate again, concatenate, and then have the root. And then hopefully the root is the same as what I committed, and I can say, oh yes, indeed, you did commit to K. Okay. Two things I want to, so are we clear on that, or is there any question around that at this stage about Merkle root and Merkle tree? Okay, cool. So few things to mention here. So first, to prove so if Ali is committed to this Merkle root, to prove that K is indeed part of the tree, she only needs to reveal K and the blue boxes, which are hashes. So she didn't reveal any of the other data. She didn't reveal A or B or L. She just revealed hashes. So that allows her to keep all the other leaf or the other data private. She doesn't need to reveal that. Another thing is that in terms of optimization, if you do a lexical ordering of all the hashes, then you don't have to tell, so I don't have to tell Bob, okay, HIG is on the left or on the right. You just do lexical ordering so that Bob, you can just then have HL, HIG, HMNOP, and HABCDFGEH just ordered. It's just the order of the hash, and Bob can know how to concatenate things. Okay. And finally, so on this image, all the leaves have the same depth. but you don't have to have the same depth. Okay, so for example, here, this could be HZ. So I could just have a Z here and calculate the hash HZ and just have a depth of 1, 2 for Z while keeping the depth of 1, 2, 3, 4 for the rest of the data. Okay, so it needs to be binary. Okay, you don't want to concatenate more than 2 at a time, so it needs to be binary, but the depth of one leaf can be higher or lower than other leaves. Okay. Yeah.
For the lexical ordering, you still need to say which depth level a hash is, otherwise it doesn't work, right?
You can, but no, you know it from the number of hashes I give you.
Okay, you just process them in order. Yeah, makes sense.
Yeah. All right, cool. Now, oh wait, wrong slide. Now, MAST, or Merkleized Alternative Script Tree. So, or MAST is just MAST. So what the hell is MAST? Exactly the same thing. It's just that my data is a script. That's it. So my data is a script, and I hash my scripts, and then I can build my Merkle tree. Okay, so that's my MAST. In the Bitcoin, so of course MAST will come with other characteristics, around. So like we use SHA-256 for the hashing. We do the lexical ordering of things, and there's few other data added in there. But like MAST per se is just a Merkle tree of scripts with specific some added properties for Bitcoin purpose. All right.
Quick question. The script here, is that a hash of the script, or is it the actual script?
Well, you start with the actual script, and then you hash it, and you have your hash of the script.
Okay, yeah. And the ordering is based on the hash of the script.
Yes, correct. The hash is. Yeah.
Thanks.
No worries. Okay, so now we can finally talk about Taproot. So Taproot, there is 3 BIPs, Bitcoin Improvement Proposal. So 340, 341, 342. So I'm just going to go in order of the BIPs. So 340 just introduce Schnorr signatures. So he mentions the fixed length encoding, like defines the encoding, 32 bytes for public key, 64 bytes for signatures. It sets the Schnorr parameters, because Schnorr is a signature schemes, and you can use different parameters to have Schnorr. So in our case, so what we're saying for Schnorr is that we use the same curves than currently, and we use same functions as currently. So same, so the curve is SegP. And so same than, yes, that's correct. So same than what we do with ECDSA, which is a SegP256K one curve, and the same hash function, which is SHA-256. Okay. We also, in there, it's also defined on how we sign messages and how we verify messages and how we derive keys, because we do some extra hashing and things like that. What we also introduced with BIP 340 is a tagged hash. So as part of MAST, as part of signatures, as part of various different in various different contexts, we use SHA-256 in Bitcoin. So just to ensure that the hash value, the hash of a value is not reused in a different context, then the tagged hash is introduced. And so it means that when we hash the value, actually what we do is that we hash the tag, concatenate it twice with value, and then hash this result. Okay, and the tag can be tap leaf, it can be tap branch, it can be tap tweak, it can be BIP40, I think BIP40 challenge. So it's just like a free text, and just to be sure that hash values are not reused in the context that it's not meant to be used.
Why are we concatenating it twice? What's the point?
Just to ensure that, just probabilistically speaking, just to ensure in case, some other software today concatenate already their value with the hash of transient or the hash of network or P2P network, you don't want to have a collision. So the idea is that in case some software already do this tag hashed with the same tag as Bitcoin, just to ensure it's not happening, is being twice. That's my understanding.
Sounds like a very weird design decision. If you want to make it specific to Bitcoin, why not concatenate Bitcoin with it?
Well, because people already do that for the mnemonics, for example. Or let's do Bitcoin seed. So now, in the context of Bitcoin, in the context of Bitcoin, some software already use this strategy. You can read the BIP for more details. We can have a look. We can jump to the BIPs later for the justification. Yeah. All right. So now next BIP is a BIP 341, and this introduces Bitcoin script update SegWit v1. So today we have SegWit v2. V0. So the first SegWit was v0. So now we introduce the second version of SegWit, which is v1. So in this BIP, we define our mast, our Merkleized alternative script tree, and how it should be built and some characteristic. We introduce Taproot, which is so Taproot output, where you can span by key or optionally with the script. It also introduced a number of unused bits for future extensions, via soft fork. So it does cater for a number of scenarios where we may want in the future to have new features. And we already have that discussed now so that it can then be done later with a soft fork. And what we discussed, as part of Taproot, the public key is used in output and not the hash of it. Okay, so pay to a public key hash, we hash the public key, and that's what we put in the output. With Taproot, we have a public key directly in the output, not the hash of it. So why is this BIP? So few things. So with Schnorr, oh yes, of course we use the Schnorr. Of course we use Schnorr in Bitcoin there. So why is that? So few things. So signature aggregation, which allows you to do so multisig, M of M, threshold signature. So threshold signature is not it's experimental at the moment, or it's like research not finished for M of N kind of a schema. But what's important is that these schemas, or whether it's single sig, it's all indistinguishable, because at the end of the day, it's going to be one public key, whether it's a single public key or whether it's an aggregation of private keys and a signature. So you increase privacy from this aspect. The batch validation. So as we discussed for the aggregation, so a miner can, any node can then verify that all the Taproot transactions are valid by adding the signatures and the public key and doing one signature verification for the whole block. And then safe space. So as we discussed with public key hash, you have to reveal the public key and signature to be able to span the output, because you have a hash in the previous output and not the public key by itself. So with Taproot, because you have the public key by itself in the output, it means that in the witness stack, you only need the signature. You don't need to have the public key and the signature. And why as well is because with mast, you don't need to reveal the full script. So as we said, and we're going to go in more detail after that, but you can have your, if you want your transaction to be able to be spent in 3 different manners, instead of having if branches, you can just have your mast with 3 leaves that are the different manner you want to span it. And when you want to actually span it, you just need to reveal one of these leaves, and you don't have to reveal the other scripts. But we go in details now. So generally, spanning an output, Taproot output. So as we say, Taproot output is SegWit 1. Okay, so it means that when you have a transaction that has a Taproot output, you can see directly it's a SegWit v1. Okay, so that's clear. In the scripted key, you put a 32-byte public key Q, which is what we call the Taproot public key. So in your output, the address is a SegWit 1, and it only contains a Taproot public key Q. All right. And then you have P, which is your Taproot internal key. And that's your key to span the output if you want to go via the key spanning. Now, how does it go? So tap tweak is the Merkle root of your tree. So if I first calculate tap tweak, so it's a hash of your public key P concatenated to the Merkle root. Okay, and you have your tap tweak. And so Q is equal to P plus tap tweak times G. All right, G being the generator, I think, on the elliptic curve. Yeah. All right, so if you just use the public key, your private and public key are small p and big P. But in your Taproot transaction output, you are going to put Q. And now my brain just exploded. That's how you end up having one public key and be able to commit to scripts and single key spanning. It's amazing. I'm just like, all right. So public key. So if you want to span using the public key, okay. So on the witness stack, you are just going to put a signature for Q, for public key Q using little q, a signature of your transaction. As usual, depending on your sig hash, you sign different things. So to check the signature, so now I don't have. How do you get little q? That's the thing, because I have little p and big P. All right. So little q, well, is equal to little p plus tap tweak. So I'm going to use then my little q to sign and put that on the in the witness stack, and then the transaction, and then because it's magic thingy, so little p is a private key and big P is a public key. And if you add tap tweak to this one and you add tap tweak times G to this one, then this is another. So Q is a valid keeper here as well. It's a matching keeper. So it means that then you have your Q and you can use Q to sign your message, and someone who verifies transaction is just going to verify that it's a signature valid for Q. So actually you don't even reveal P at this stage. Like it's just look at normal signature, and the fact that you can span by script and by public key, and that we have a tap tweak, which is our Merkle root, behind the scene, is something you can't even see on the transaction. Okay, and that's how you can span by both script and public key. I was amazed when I understood that. I was like, wow. Okay, so now the other way to span via the script. Okay, so if on your witness stack, if your witness stack has more than one argument, then we assume we are going to span by script. So on the stack, you have the arguments of the script, the script S that you want to use, which is one of the scripts in your Merkle tree. You don't know which one. It's one of the scripts in the Merkle tree. You say, I'm going to span with this one. You don't have to reveal any other script. And you have the control block C. The control block C contains a leaf version, so I will talk about that later. It contains the Taproot internal public key and the Merkle proof, which is basically the sequence of hashes. So to verify the transaction valid, so first we're going to check the Merkle proof, do what we said, get the hashes, concatenate, hash, confirm that it matches the tap tweak. And then we are going to check that Q equal P plus tap tweak times G. So you reveal P, all right, and you have to verify because you have Q, on the output. So by revealing P, it allows the validator to verify that this Merkle root is the one we committed to, and then you can run the script. Boom. I don't know if you're as impressed as me, but when I understood that, I was like, oh my god, this is insane. Okay, so any question so far? This is basically like these two sides were basically the core of Taproot.
One question regarding threshold signatures. I can basically simulate threshold signatures by just having all the different combinations as M out of M signature scripts, right?
Exactly. Yeah. So okay. So let's jump to the next one. So maybe
get a question first.
Yeah.
If you this control block C, if you can always just pass in one script, or can you pass in multiple scripts to validate?
No, you pass one script, which is the script you're going to use to span.
Okay. And do you know the size of this witness stack then compared to the old witness stack? Because now it looks like it grew. Because in old witness scripts, you had arguments and a script. Now you also have to pass in the control block.
Yeah. Okay. I'm going to answer that in 2 seconds.
Okay.
Any other question at this stage?
No.
Yeah. So you both pointed out to something. So I'm going to jump here. All right. So key spanning should be default. Okay. So that's not the consensus here. That's more of like advice. You should always make the key spanning the default. So for example, let's say you do a multi-sig and it's 2 out of 3. All right. Let's say business partner, 3 business partner. So what you should do is that in this case, you should put the P, for the key spanning, should be the aggregation of all 3. So that if everyone agrees with spanning, then everyone sign and you do key spanning and you're good. And maybe in the case of one of these business partners is unavailable, then you want to have the script. So let's say we have Alice, Bob, and Carol. And so in your script, as Thomas said, you could have one leaf which is Alice plus Bob, one is Alice plus Carol, and one is Bob plus Carol. To say by default, we are all 3 here, so we all sign, and it's a public key. But let's say one of us is away in holidays, it's not reachable, then we can still span because we will do a 2 out of 3, and in this case, we use the script. Now, as I mentioned, let's say, for example, that Alice, Bob, and Carol is your wallet. So maybe Alice is your hardware wallet, Bob is your phone, and Carol is some mnemonic you have on a bifodal at your grandma. So in this case, Alice, so you are going to use your phone and your hardware wallet most of the time. So the span key should be, sorry, we need to add the 4th one, for example, to work. And we have David, which is another seed in the bank vault. Okay, so you have 4 keys and you do 2 out of 4, for example. So by default, you want the span key to be your phone and your hardware wallet, because that's what we're going to use all the time. Now, sometimes, like when you change phone, maybe you use your wallet all the time. So you do go to grandma quite often to do the 3rd one. So in this case, this one could be just 1 depth on the Merkle script, so that you only have to reveal 1 hash. But let's say you have other backup, bank vault, accountant, buried in the mountain, and you actually have so many backups that you have more Merkle paths. So this one can then be on the second branch of the tree and have a depth of 2 or 3. Where if you use this one, then you have to put more on the stack, more hashes on the stack. So let me try to summarize here. So basically, in short, you want to try to make whatever is the most likely scenario for you to span output. You should try to put that in P, in your public key, and you can use aggregation for if you want multi-sig. Now, if you look at once you've done that, then you look at building your mast, and you can think, okay, I want 3 ways to span that, but 1 way is the most likely one, and 2 other ways are least likely. And so in this case, the first branch should have the 1 way, and then the second branch can split into 2 other ways. So that if you use this first way, then you only have to reveal 1 hash, right, for the proof. Does it make sense? And I jump to the tree. So
yeah, keep talking. Sorry.
Yeah. So let's say, let's say 1 way, most likely it will be this way, all right? And I have more ways to span, which are maybe like that. Okay. So it means that if I'm using this script here, I just have to reveal this hash. So I just need to put 1 hash on the stack. And then the validator will take this hash, concatenate hash, and then it has a root. But I'll also have all this way to span. But if I want to use one of these ways, then I have to reveal 1, 2, 3 hashes. 4 hashes, sorry, on the stack. So I have to put 4 hashes on the stack. So it means that you can work with probabilities and like, okay, but the least likely way for me to span is going to cost me, it's going to be with the biggest transaction. But again, it's all on the witness stack, yeah? So it's not part of the transaction with SegWit. So that's called a Huffman tree. So Huffman tree is where like the depth, like not all the leaves are the same depth. So you can say, for example, the first leaf is depth 1, and then leaf 2 and 3 have depth 2 because they are together on the second branch.
But this doesn't mean that you change the order of the leaf, right? It's just you have a different, you choose the depth. Or can you repeat what you just said, please?
You rebalance the tree based on probabilities.
Yeah.
So like you have your left branch from the top is only one level deep.
Yeah.
And then all the other combinations you arrange in pairs on the right side.
Yeah.
And you arrange them so that the more likely combinations are further up.
So you can have a script
sorted
here.
anymore then. They are not sorted. Initially, you said they are alphabetic, lexically.
Yeah, that doesn't matter. Yeah. No, but
the lexical sorting is something different.
Yeah, you can still do the sorting. So I will put a script here. So I put a script here, okay, on my blue box H, A, B, C, D, F, E, G. So that's one script. And then I put all my other scripts here. Okay?
Yeah.
So I hash them, and the hash, I order the hash here. I order the hash here. I order the hash here. And then I order this hash and this hash. If then it gets swapped right to left, doesn't matter. What it matters is that if I want to span this script, I only need to reveal one hash. Or if I want to span this script, I have to reveal 4 hash for the proof.
So the lexical order of H, A, B, C, D, F, G in this case, the leaf on the top left, does not have to be smaller than HI.
No. It's for the same level. So it's so that you know how to concatenate. It's to know whether you concatenate this one left and this one right, or the opposite. So you concatenate. Yeah, the lexical ordering is more for the concatenation. Always concatenate in lexical ordering, so you don't have to think, oh, which one.
I thought the whole tree is sorted.
No, I think, I just took the same terminology, but in short, it's just that when you concatenate, to know which one goes left and which one goes right, you just use lexical ordering. So, so it means that, so to give you a proof, I can just give you the hash. I don't have to tell you, oh, this one is for right, this one for left.
Because you can basically walk through the list, right?
Yeah.
You have, like, let's say you have 3 hashes, and you have the initial script. Then, and you know it's always in pairs. So you hash your script, and then you lexically sort the hash you got with the next one, and you hash it again. You lexically sort that one with the next one, hash it again, and once you've been through the list, it has to be the same as the Merkle root, otherwise it's not valid.
Yeah. Okay. So then, so Merkle leaf is actually, it's not a script, it's V, which is the leaf version, concatenated to the script. And that's what we hash. And we go back to the leaf version. I just wanted to introduce the leaf version. So the leaf version, so back to there, you have to specify the leaf version when you want to span. Okay. Now, so one of the also advice is to avoid op-if. Okay, if you are using op-if or op-not-if to specify different way to span the transaction, then you should just have different scripts in your tree. So like HTSCs, we have in our HTSCs we have an op-if, and in the witness stack we put 0 or 1 to say, oh, go in this branch of spanning or this other branch of spanning. So here, don't use op-if, just have different scripts. Okay, so it means that. So back to what we discussed, if we do, let's say I do HTSC. So HTSC is not the most clever thing to do now, but let's say we keep HTSC, and let's say we keep, we put the full HTSC in the market tree. So you have one branch where you verify the hash, and one branch where you check the expiry. So now, if I say I want to do refund, so I go on the expiry side of things, I will just review the expiry. So from an outside observer, they don't know if this was a failed atomic swap, or was it a backup system where I only span with one key, but I lost my key, so I can span with other keys instead after a certain time. Like, you don't reveal anything. You just reveal the branch, the spanning branch that is needed to that you want to use. Something else is that sig hash in Taproot is now called hash type. The same values are used, except that a new default type is used. So 0 is the default value, and it's the same as SegHashHole, the same behavior as SegHashHole, which is also 1. We're just like introducing a default type now. So by default, it's SegHashHole. Then in the witness stack, there is an annex A. So annex A can be the last element on the stack. This is introduced for future soft fork. So at this stage, it's recommended to not put any annex A, but in terms of consensus, if the last item on the stack starts with byte 50, then it's annex A and it's discarded for now, and it continues to do your script or your spend by key as usual. And then finally, you should always include the key and script. So, and again, that's to help with heuristic and analysis of the blockchain. So even if you say that I just want to spend money with my key, you don't want to put P as Q. You still want to have a tap tweak. So even like you still want to have a tap tweak, and it just the BIP explained to you how to create a tap tweak. So in this case, I didn't put it here. So in this case, it tells you I didn't put it here how to calculate tap tweak, which is using P. So you create a random hash basically like with your P, and you still put tap tweak in there because if you put and same for if you just want to span your script, same thing that you just put an unspendable key there, but not a fixed value either, because then if you have a fixed value unspendable key here, a fixed value P, then the heuristic can see that this output is only meant to be spanned by a script. So again, it shows you how to create an unspendable P without revealing that it is unspendable. But the way it's done, you can still reveal it to someone else. So it's just a lot about privacy basically, and trying to reduce heuristic analysis. So it shows you. So BIP explained the method on how you can create an unspendable P, but still prove to someone else that this P is indeed unspendable. Yeah. Yeah. Now, any questions so far?
One comment. To answer Philip's question from before, the stack gets smaller because you avoid all the op-ifs. So like, yes, you add more Merkle, you add more hashes to it, but overall, your average witness stack is a lot smaller because you're only revealing the branch of the script that you're actually spending.
Yeah.
Assuming you have big scripts, but for a simple script, it grows. Like if you only have a hash lock without time branch, then the stack is bigger than using SegWit 0.
Well, you would have a signature anyway, right? And the signature is you still have a signature here.
The signature is smaller now, right?
It's smaller by a couple of bytes.
By 64, 70, it's by 6 bytes. But wait, that's all on the witness, right?
Yeah.
Witness stack is so you don't pay the fee for that.
Okay. Because that is dropped then?
Because it's SegWit, segregated witness. The witness is not part of the fee calculation.
Yeah. Okay.
Well, it's only to 1/4, right? Or is it not included at all? I think it's only
validated, and then no. Why is it not part of the fee? Okay.
It is, but only to 1/4, I believe. Right, like the weight units are calculated by dividing the overall size by 4. So, like,
no, that's the transaction size, not the witness stack. I think you don't.
Let's go back to that.
I don't think you take into account the witness stack in the size.
Yeah, let me. Let's go back to that. I need to double check the wiki. Okay, let's go back to that. Okay, so then the last BIP is B342, and it's just so it's about the script by itself. So there's few changes, and that's only for Taproot. Okay, and as you can see, it's SegWit v1, so there's no possible confusion. So in short, it changes Object-Sig and Object-Sig verify to be for Schnorr. There's some improvement around opcode separator, which I haven't been able to look too much into this opcode, which was already existing. Object-Sig multisig and Object-Sig verify are disabled, so we can't use that in Taproot. Instead, you use new opcode Object-Sig add, which allows you to do the aggregation. And there is a new number of op success codes. So this op success opcode is like the replacement to the no op. So if you encounter an op success code, when you decode the message, so when you decode your script, then automatically the script is successful. So that allows, so it means that if you want op success in the future is it's replaced by a new opcode, then it means that all the old node will just consider the transaction valid, and the new node can apply the new opcode behavior, which is, yeah. And then, so at the moment, the leaf version is set to C0. So we said that for a script, there is a V version. So I haven't read too much about that, but my understanding is that it allows you to version the scripting, So at the moment, we do C0, and then as future, we can change the version there. And then finally, maybe something interesting for us is that if you do end up still using op-if or not op-if, then you only accept 1, 0, which is array with 1, or empty array of the witness. Because at the moment, op-if is valid with any positive number, and op-not-if works with 0 and empty. So it's called minimalist. So just having this minimalist behavior just to avoid any script bugs. Yeah. Yeah. Any questions on the opcode? Okay. And then finally, there are some changes in terms of resource limits. So I just wanted to mention it. So the script size limit has been removed. So before there was a 1,000 byte script size limit, so it's been removed now. A script is still limited by the size of the overall size of the block. Then there was a limit before as well on the non-push opcode, so that's been removed as well because it's also limited by the overall size of the block. There's a TabScript sig op limit. So to avoid consuming too much CPU by having a reasonable number of signature operations, the number of sig ops, which is like signature check, signature add, and things like that, is limited by the number of signature on the witness stack plus 1. So that's like, the calculation is a bit more complicated than that, but in short, that's the gist of it. So the idea is to say, if you put 5 signature on the stack, then you can do a maximum of 6 signature operation. And you can't have a script that is going to try to do extra signature operation and try to consume extra CPU there. And then stack plus a stack element count limit. So there is a stack limit which is already existing, which is 1,000 elements. But now the initial stack is included in there, which was not the case before. And same for size limit, same thing. The size limit per stack element is still present and also applied to the initial stack, which are what we call before the arguments. Yeah, that's pretty much it. Okay. Yes. So I think for the witness, so the witness is just smaller. Exactly. It doesn't count for the quarter of its actual size for SegWit. Just quickly checking the Wikipedia.
Sorry, can you repeat that?
So the witness stack count for 1/4 of its actual size.
Yeah, that's the weight then.
Yeah, and you use weight to calculate the fee.
So that means the raw transaction size increases with SegWit version 1.
Yeah, but if you span the script, Depends.
If you have a complex script, okay, but for a simple script, let's just take the hash lock. The transaction size is bigger because you have to add more data.
Well, your default spending should always be the key, and for that it's smaller.
The point is that with a hash lock,
yeah, Frank,
you well, it's not sure because like in your
the
case,
hash lock with a adapter signature, right? So
well, yeah, you shouldn't do has that, but like if you you should do PTSD, but at the moment, if you have a script, you still have to, like in the HTLC case, you have both branches. And when you reveal the script with both branches. The idea is to say, when you have even your example doesn't really apply because we don't have nobody does a hash lock where there's just a hash lock.
Sure. There are hash locks. It was the first.
Why would you do that?
Because you want to lock something with a secret.
You mean a hash lock without a signature?
Yeah.
Why would you do that? The miner can steal your money.
Yeah, okay, then add a signature just to make sure. It's still, you don't need the time lock to make a hash lock useful.
Yeah, but a hash lock plus signature can always just be expressed as a signature. It's just another secret, right? It's like might as well just include it in there.
Okay, yeah. So you shouldn't use this construction. Okay.
But I mean, for the sake of the argument, it might be slightly bigger, yeah, but it's probably not by much because you have savings on other ends, right? You don't need to include the hash of the public key, for example, whereas in previous versions you had to, and stuff like that. So
I just remember the debate back when SegWit was activated, and the miners were complaining that the transaction size wasn't reduced. It was only the size it took in the block was reduced, as you said, the weight divided by 4, which meant they were losing out because you paid less fee for the same space. And I just wonder if we have the same problem again.
So I doubt it, because you can sell them on the signature aggregation massively, because that consumes CPU power, versus the other thing is just storage, and storage is cheap.
Yeah, so that was the argument back then, that SegWit introduced the requirement on CPU power because you had to validate more transactions for same space, same cost, basically.
Well, and Taproot saves you now on CPU power.
Yeah.
Because you can aggregate the signatures. So
if
seems
we
like
discuss,
a better outcome.
Yeah. So if we discuss about PTSD, for example, so so first you don't want to do HTSC anymore, you do PTSD, right? Because now what you can say is that, okay, so I'm looking against a point, and that's your P, the P of the, that your default spanning, it's like spanning by key. So the idea is that, if you do atomic swap, then this secret key you want to reveal, you want it to be P in your Taproot, so that you can just then sign your transaction normally. And then if you still want to have a refund pass, then in your Merkle tree, you can have just one script, which is your refund. And then so that you have to reveal the script to do the refund based on the time lock. So that by default, it just looks like a signature, and you can still have a script, but the script is never revealed if everything goes well.
There's one argument against the PTLC, and that is it's an interactive protocol, versus HTLCs are non-interactive, right? If I just know the hash I should lock against, I don't need to talk to you for that. I can just do it.
Well, you needed a hash in the first place.
Yeah. But
Yeah, I don't know how
signature is always interactive. Like you need network communication to exchange stuff. I believe.
Yeah.
At least that was Andrew's argument when I asked him what you need miniscript for when you have adapter signatures and these kind of signature protocols. And his argument was that they require interaction versus any script is basically always non-interactive. At the time when you spend, you no longer need to talk to the other guy for any kind of information. So cold storage and stuff will always use scripts rather than funny signature tricks to mimic several spending conditions.
I wonder now, considering how it's considering the could you have just a secret in the script?
No, because then the miner can steal it.
No, with a signature.
What do you mean?
Instead of having a time lock there as well.
No, like you can have like the hash pass. So yeah, of course you have one script with a time lock, and then another script. I was just thinking because you don't need to. You need to review the script. No, you still have to have a hash and signature in there. No, it's the same actually because you end up with the hash of the script in the leaf, and you have to prove that you logged against that. Oh wait. Yeah, you have to prove you logged.
If you know the secret ahead of time, then you're not locking against anything.
Yeah. Okay.
Right.
Anyway.
Like, at least no one can verify what you locked against. If it's just a secret, anyone you trying to convince that you locked against something will need to know the exact same value, and then it's no longer useful.
Yeah, you have to reveal the full tree. You can't hide anything to the other party.
Exactly, and that's why you still need a hash.
Yeah, so so instead, so it's a bit more complex. So you have to, or you have to agree in advance on how what is the tree structure for HTSCs. The same way that you agree on one script, you have to agree on the full master.
All right. So when miniscript for Taproot.
Yeah, so the interesting thing here is that there is similarities with miniscript in the ways that how it's simplified, because with miniscript you can put probability or weight when you in your input policy, so that the script will try to optimize to make the branch you use most the cheapest one to use. But here it's even simpler because the branch you want to use most, that there's the one you want to put of depth 1. So let's say if you have 5 branches and there's one that is used more than the rest, then you want to have a depth of 1 for this branch, and then put the other 4 on a second tree that will have a depth of 2 or 3.
So that means you can actually create a miniscript compiler that will output you a Taproot tree.
Yeah, I expect it to be I expect it to be very easily compatible, because it's the same way that today you specify to your miniscript input different way to spend your coin, but instead of having results which is going to be a mix of if up and whatnot, it's just going to be amassed with the various way to span in branches.
Yeah.
On the OR side, and of course, if you have an AND, the AND needs to go in the same script. Yeah.
Little brain exercise. What would change in our transaction structure for Monero Bitcoin atomic swaps if we use Taproot? I guess the amount of transactions still remains the same, because that one has some game theoretical reasons. The only change is that we use Schnorr signature aggregation instead of 2 out of 2 multisig.
Yeah.
Lucas, what do you think?
And and the all the punished transactions, are they using a script? Is anything using a script?
Only 2 out of 2 multisig. The time log is on the transaction level. We could actually move the time log inside the transaction, inside the script, the tree, so that from the outside you don't see that the transaction has a time log on it.
Yeah, so that's the thing. So let's share the. Can you see my new screen here?
No, you can't.
Yeah.
I don't think you can, because a time log inside a script will still always reference the value that is stored in the nlog time field. You just trigger it through the script, no?
Okay, so
I always
TX log.
confuse those two. I think there's a different field. There's the nlog time field and the n sequence.